Any questions from last time? So last time we were talking about the connection between integrality, valuation things. In fact, we had this big theorem. Suppose R is domain, function field K. Then your closure of R is equal to the intersection field, or I'm sorry, the integral closure of R is the intersection of all valuation overrings, which is close to that. Proof. Last time we showed that R is contained in intersection of valuation overrings. Which wasn't too taxing. How about the other? Suppose that alpha lives in the intersection any strategy ideas? Oh, also. Alpha is integral over R if and only if so remember this result. I think I had everything kind of flip flopped. I think the original results in the notes is alpha inverse is integral over R, if only alpha inverse is in R alpha. 6 1 half dozen the other. So how does that help? I mean, I guess what my main, what I want to do is I want to show this containment, I want to show that if alpha lives here, it must be integral. And this is a useful, I hope, characterization of what it means to be integral. Right? How does that help? Well, right. So this gives us the polynomial, but what about we want to show that alpha is in R alpha integral, right? And what do we know about alpha? We know it's an evaluation over. Right? What else might we bring to bear? Okay, recall. Well, all the evaluation of the brain. Okay. We also know. If alpha is a unit in R, then alpha is in an alpha inverse is in R. So alpha, right? So we're done. Alpha is a unit in R. Everybody okay with that? If not, uh, alpha survives in uh, like alpha survives in R alpha. Uh, uh, so we can assume, so like, let me, let me word this more clearly. Note also, if alpha is in R, which is contained in R alpha inverse, then we're done. So we can assume that alpha is in every valuation overring, but it's not in R, and we need to show that it actually is in R alpha. So that's kind of putting everything compactly where we need to be. Suppose so let's suppose that alpha is not in R alpha. That's basically what we did. So alpha is an element of the quotient field that's not in R alpha inverse. And let me give you a hint. We're going to go for a contradiction here. The contradiction where we want to end up is finding a valuation overring of R that doesn't contain alpha. If alpha is not an R alpha inverse, then alpha uh, if alpha is not an R alpha inverse, then think about the ideals. Right? Because the principal ideal generated by alpha inverse, notice alpha inverse is of course in this room. Right? The principal ideal generated by alpha inverse must be proper if alpha is not in there. Agree? I agree. So there exists a valuation which valuation overring, which alpha inverse survives, right? That was probably one of the last theorems last time. Remember that one? If you have an ideal and a ring, in this case, the ideal generated by alpha inverse in this ring right here, if it's proper, there's valuation overring of this ring in which this ideal survives. Great. But this is also an overring of R, because R is contained in R alpha inverse. Correct? Anybody see what the problem is now?
Or if alpha was its valuation domain, then an alpha is going to be a.
That's correct. Good, good. Since alpha inverse of, let's say, let B be a valuation domain in which alpha inverse B is proper. But then alpha cannot be in B. For if it were, then this would contain one and it would be proper. This is a contradiction as alpha and B for all B containing R.
Everybody okay with it?
Therefore, the intersection this is a wonderful theorem because it takes a property that is crazy crap about roots of polynomials and roots of monic polynomials in the quotient field, and it turns it into an intersection valuation domains. This is one of the things why, or one of the reasons why integrality is so important. By the way, just for fun, in your homework, I asked you some questions about this complete interval closure, right? Which is, it turns out that, in fact, you can use this theorem. If you take a ring if you take a ring R and you take its interval closure, that's an intersection evaluation overrings of this, right? The interval closure of that is the same. So once you go to the interval closure is interval closed. You can prove this directly. You can prove it using this characterization, etc. It turns out the complete interval closure of a ring, so you take everything out, it's almost interval, is intervally closed. But it's not necessarily completely closed. All right, so here's a famous example by Gilmer and Heinzer. But R, any field F, let's see if I can do this. No, it's just this. This is a really weird example. I'm not going to go through a lot of details, but I think it's worth looking at this. Let me kind of give you just an idea. Notice that the powers of X in this that I'm adjoining. So I'm adjoining monomials where this is growing linearly and this is growing quadratically. Right? So the first one is yeah, excellent. I guess it's this one. It's X. How do I index this wrong? So this would be X, is right? And N equals 1 is X squared y to the 1. So help 0. So this would be X. This would be X squared y to the y squared, right? From about 3, let's see. Then it would be X cubed y 10 X4 y to the 36 like this. And so it's anybody tell me what the quotient field of this is? think maybe I started. Oh, oh, my bad. It's been a while, so here we go. It's x to the 2 equals 1. Y, you know, that's what it is. So I'll start. Invert that. So, this is f. I start at 0, I get x, then I get x, x cubed, y cubed, I get x to the 5th, y to the 10th, x to the 7th, y to the 21. Okay, so what's the quotient field of this? Well, okay, can you help me out a little bit? I mean, what's the quotient field contained in? Sort of an upper bound of the quotient field. Certainly, everything is contained in the polynomial, right? The question is it that big, right? So for example, if I had something like the quotient field of this is not f round brackets x, right? Because there's no way to get an x in that quotient field. So the question is really, I know I've got the f part. Do I have both x and y in the quotient field? And if the answer is yes, then I think I've everything. Right? Well, I certainly got x. Do I have y? You actually do, but you gotta work for it, right? Because of this, you have y cubed in the quotient field, right? And because of this, you have y 10th in the quotient field. Now run the Euclidean algorithm on this. Take this and divide by the cube of this, and you get y. All right? Do I agree with that? So actually, the quotient field is f x squared. But so if you look actually at the complete interval closure bar, you might tell what this is. Let me help you out here. The defining polynomial this means, in fact, x, y, n is in the quotient field is integral. And so therefore, it's almost integral overall. This is actually everybody okay with that? As it turns out, this ring is actually interval closed. When you take the complete interval closure, it's interval closed. But this ring is not completely interval closed. But now notice at this stage, y is almost infinite. Because X is a non-zero element and every power of Y times X is equal. Do I agree with that? So the complete integral closure of the complete integral closure is F X Y. And FXY is a unique factorization domain, and they're known to be completely integral closed. So you're done with this step. So when you take the integral closure ring, you're stuck immediately. Integral closure is integral closed. Complete integral closure. Here, you jump 2 steps. And in fact, it jumps a bit of a cheat because the first step is actually just the integral closure. Come on. And then the second one, you jump further. And in fact, you can construct these things so that you jump in times, which is kind of weird. But, so here's the whole reason I brought this up. The integral closure of the integral domain is the intersection of all its valuations. That's the integral closure. The complete integral closure is integrally closed, so it is an intersection of valuation domains, just not all of them. Which ones do you throw out? Because the complete integral closure tends to be bigger, so you throw out some of them. Nobody really knows the answer to that. Which ones that you throw out in general. Okay, any questions? How many of you have ever heard the buzzword invertible ideal? Right, across your path? Oh, well, I'm here to say today. I think that I think Jared discussed some of this stuff. Did he talk about the failed attempt at Fermat's theorem's proof in 1847 by Lemay? Right. Problem was, well, in fact, let's just say prime. So I can say here. So it was a failed attempt from Fermat's theorem. So this is kind of a little historical there. Using this field, the idea was to take the equation x, well, it had been shown that if you could prove that if there's, Fermat's theorem will hold if you show 2 things. For any odd prime, this has no solution. And for the case for n equals 4. Right, so if there's no solution for x of 4 plus y of 4 equals z of 4 and all odd primes, then Fermat's theorem is done. The case for n equals 4, it's very famously done by infinite descent. It's done a number of ways. So they toss that out. And the case for 3 was done separately. Some other cases historically kind of popped up. There was a proof constructed from May, I think it was 1847. The idea, of course, is this ring has a primitive P3 unit. So now you can break up the side of the equation as some product x minus the plus tornado I cross I. Use some yin yang about prime factorizations and argue that you can't have a solution. That was the whole The failure of this came. The proof worked great, actually. The failure of this came from the fact that this is not a UFD. So when they were doing decompositions, they were assuming that you had unique factorization. That was the lever that they were pulling. Unfortunately, that mathematical structure, Z adjoined with this thing, is not usually UFD. It's always full ring of integers for people to be, but it's usually not a UFD. In fact, but you'll see what the problem is, I think. Back then, they were doing a lot of stuff by hand, right? In fact, this is a UFD. If and only if P is less than 20. So this works all the way up through prime 19, and then it fails at 23, and it fails for every prime. It's never good. So, as it turned out, the proof could be modified, the original one that was wrong. And it filled in a hole. You can modify this with, you didn't quite need this to be a UFD. You needed, well, you needed the prime to be regular, what they call a regular prime, which means this is some terminology that will come up later. What it means for a prime to be regular is it does not divide the order of the class group of the ring from which it comes. If this is UFD, the class group is always trivial, class number is 1, and the prime will never divide it. This prime actually is regular because for 23, this has a class group that we would talk about in 23.53. There are only 3 irregular primes less than 100. So they're the usual, right? Regular. So Fermat's theorem is actually not showing for all regular after they adjusted back. Here's the sad part of that story. As of right now, or well, as of the last time I checked, which was a 2 month, it is known that there are infinitely many irregular primes. It is not known if there are finitely many regular primes, or it's not known if there are infinitely many regular primes. So that is a case, I think, of the terminology being assigned a little too early, perhaps. But anyway, so what happened? What happened was unique factorization failed, so the proof failed. But then it was adjusted using some of these ideas. UFDs are really cool. They're very robust, very strong rings. In them, what happens is you have every non-zero, non-unit can be written uniquely as a product of primes, up to 3 arrangements. Right? Here's another way to put this. In a UFD, every principal ideal can be factored uniquely into a product of primes. Every non-zero principal ideal, product principal ideal can be factored uniquely into it. In a PID, this is even stronger because in a PID, every ideal is prime. So now you can say every ideal can be factored unique, every proper non-zero ideal can be factored uniquely into a product of principal prime ideals. And so one way to generalize this, you pass from the element-wise talking about prime factors, you pass to ideals. So a Dedekind domain is sort of like the 4-person version of the UFD. Maybe you can't factor non-zero, non-unit elements uniquely into prime elements. But what you can do is you can factor all non-zero proper ideals into a product of prime ideals, right? So that's kind of the philosophy behind it. But to talk about this, we need to first discuss what I mean for an ideal to be inverted. So let's get started with this definition. Let R be a domain, of course, to K. And we say that I and R submodule K is a fractional angle. If there exists a non-zero A in R that's, okay, so what this is this is a finite distribution. Let's look at some examples. First of all, note any regular ideal because an ordinary ideal that you're used to is certainly an R submodule of the quotient field. It's contained in R, so it's contained in the quotient field. And it's a module because when you multiply something in I by something in R, it's in I, right? And here we can take A to be what? That's exactly right. We can take A to be one. Right, because I is already in R, if it's important. Let me give you another example. Notice that this, what I mean by this finite condition is I is an R submodule quotient field, so I consists of a whole bunch of fractions. So potentially this could be a huge mess, right? What this condition means is all these fractions can be brought to a common denominator. Right? So that's the strong thing about this notion of fractional ideal. It means that every element can be thought of as having denominator. So as a further example, right. Namely, two words here. So does four. In fact, any even number will work for being an A. Everybody agree with me? Q is not a fractional ideal. And the reason is C has infinitely many primes. Right, in a certain sense, that's a little fast to move because you can have larger number of powers. But that's one of the reasons I should say. Q is not a fractional ideal because there's no magic A such that every element of Q can be put over A. Notice fractional ideals. This is a Z module, right? So you add two things to this form, it's still this form, right? Any two things are something over A, something else over A is a new something over A. And notice you can multiply anything in that fractional ideal by something in Z and it's still in there, whether it's even or odd. Multiply 3/2 by 7, you get 21/2, which is further down the line. Notice, you cannot multiply two elements of the ideal necessarily, right? But that's okay, you know, people get confused about, oh, it's an ideal. You're used to being able to multiply elements in an ideal, but that's only because in ordinary ideals, both elements of the ideal are also in R. So the generalization is you can only multiply these things by elements of R. Okay, any questions? Uh, Definition, 932. Let I be a fractional ideal. We define I inverse. This is all the stuff in K that blasts I back into R. This is sometimes called the vector ideal. It's everything in K that hits I and knocks it back into R. Inverse. This is just loosely called the inverse, right? I mean, that just think of this as a terminology, so it's all there for now. Note, by definition, I inverse is contained in R. Because when you multiply anything in I times anything in I inverse, it's known as R. Right? If I inverse equals R, say it's inverted. Okay. Well, can anybody give an example of an ideal that's part of it? How about this? By the way, can anybody figure out what I inverse is for this? Yes. The inverse for this is 2Z, right? It's the ordinary ideal 2Z. Notice that when you multiply any multiple of 2 times this, it's in there. And notice when you multiply this by 2Z, you get exactly Z. So this idea is perfect. Let me make a more general statement here. Behind 0 of alpha A closure field bar. Then alpha R is fractional ideal. All right. And in fact, if notice alpha R, if you multiply this by any non-zero element of quotient, this is a fractional ideal, because alpha is A over B. So when I take B alpha, B times alpha R, that's the same thing as AR. A is a non-zero element of R, which is contained in R, so there you go, right? Anybody want to take a wild guess as to what I inverse is? We should do this computation. Do you want to guess what it is?
A first order.
How about that? Do the computation, show that this actually is the inverse and AR, or I'm sorry, alpha R, alpha inverse R. So we come away with the theorem here, and that is any non-zero principal ideal is invertible. Now, first question that you might ask is that it, right? I mean, I feel like a total tool sitting up here defining invertible ideals if they're equivalent to principal, right? Let me prove a theorem that will allow for the next example here. Proposition 934. Let I be a fractional ideal. For following equivalent. Number one, I is invertible. Two, there exists a non-zero J in R such that IJ. I can sketch this one quickly. One implies two. If I is invertible, then I inverse equals R. And there exists A and R non-zero such that I inverse is contained in R. So let J equal I inverse. The reason, of course, for this is because I inverse is fractional ideal, and IJ equals I alpha I inverse for AI inverse, which is AR, which is contained in R, which is principal. And on the other hand, if IJ is principal, then IJ equals AR. A and R not zero. Now show I inverse is A inverse. And it's okay. Any questions? We will discuss this further next time. Let me remind